Right. Welcome to this video. In this video, it's just a dive now into understanding how rational functions behave. And therefore, we're going to start with the first property of rational functions. One of the things we need to note in the rational functions is the idea that there might exist a vertical asymptote, or hence a VA, the vertical asymptote. So in a rational function, normally you'd have a function in the form of px over qx, and where qx and the most important thing is that qx is not allowed to be 0. So qx is not allowed to be 0. So where qx equals 0, that is the restriction that we have to make. And this restriction is the one that gives us the equation of the asymptote. So the equation where the restriction is what's going to give us the equation of the asymptote. Q is just any number that we can use. So let's dive deep into doing this. So determine the vertical asymptote of the following functions. All that we're trying to do is to determine the vertical asymptote. So if you're given a function like this, you need to determine the vertical asymptote. So how do we get that? You look at the part which is the denominator, which is x squared minus 4. You make that equals to 0 because that's where the function will be undefined, and that's where we find our vertical asymptote. So luckily with this one, we can easily see that x equals to plus minus 2. So what this means that we now have two vertical asymptotes, and therefore our equation of our vertical asymptote is going to be x equals to minus 2, or x is equals to 2. I will show you in a little bit later in the video what this looks like and what the functions look like. I've just sketched them on GeoGebra. Let's come back to this next one over here. Similarly, you are looking for the vertical asymptote, so it's basically where the denominator is equals to 0. Quite easy. So from here, I think you can either plug this into your calculator or you can use the good old-fashioned method of factorizing. So this will be 4x plus 4, and this will be x minus 2. And therefore, the equations of our vertical asymptote will become x equals to minus 4, or x is equals to 2. Let's deal with this last one over here. With this last one over here, we've got x squared plus 9 equaling to 0. But if we do this, we can clearly see that this will give us the square root of minus 9. And the square root of minus 9 is imaginary. Okay. So this is an imaginary number as part of our complex. So therefore, if the square root is imaginary, we say that there are no vertical asymptotes. So no vertical asymptote exists in this function. So let's see how. So I've took the liberty of sketching these graphs on GeoGebra. So the first one where it has the vertical asymptote, you can clearly see x equals to minus 2, x is equals to 2. So as part of you sketching this graph, you'll obviously have to use the derivatives and get that there's a turning point that exists there. And therefore the graph is increasing, decreasing, gets to the asymptote. And then from the asymptote, you'll see that the graph is strictly increasing in that direction, and therefore after the asymptote that's decreasing. So that's how you'll be able to calculate functions of this type. For the moment, we are just focused on the vertical asymptote. Similarly with the next function, the one that we just worked out, x equals to minus 4 is the vertical asymptote, as you can clearly see there. X equals to 2 is another vertical asymptote. And therefore, in between, you can sketch this graph using your derivatives, where you find that there's an x-intercept there, and therefore there is some form of change in the concavity there, and you can decide what the properties are. So the function of this last one, where there was no vertical asymptote, looks like this, and you can clearly see that there is no vertical asymptote that exists in this function. So this is a good way for you guys to be able to prove this. I hope this has made sense. The vertical asymptote concept is the easiest one to understand. In the next video, I'll deal with the horizontal asymptote. So see you in the next video.